Hello teacher, hello everyone. I'm very glad to stay here to talk about my topic in advanced deep learning course. And my topic is applying continual learning in sleep posture classification system. And I am Phạm That. I'm from Phoenix University. So the content that I will talk about is the first one, the introduction. Second is system and method. The third is result and evaluation. Evaluation. The fourth is discussion, and the last one we have some conclusion about my study. So sleep position is very important in our lives. So how your sleep affects the quality of the rest you get you get and your overall health. Typically, we don't choose how we sleep, and some people sleep like stated on their back. Some people, and you see in the finger, approximately 7% people sleep on their stomach, with stomach position, and approximately 40% people sleep on their back, and the rest, about 54% people sleep on their position. So, but you should know the own sleep position as good, as ideal, as good. You can train the position. You can train position on your sleep in. So why we need to monitor sleep positions? Sleep on your size offers several benefits. It promotes healthy spinal alignment, and the sleep position least likely to result in the back pain. It's especially when supported with pillow. Side sleeping when you in the finger here. Side sleeping here is good. It's good for your health, and it's good your back. It reduces sleep apnea, no compression, and better breathing. So the sleep position affects sleep quantity. It's maybe good or not good. So we talk about sleep position classification. It refers to identification and analysis of the various positions individuals adopt during sleep. And traditionally, sleep positions data was collected through manual observation or subjective self-reporting. Um, the automations of the sleep position classification offers several advantages and motivation. And in our study, we have some contribution that such as establishment of a supervised dataset comprising acceleration signals and sleep posture labels. Um, propose novel applications of the LSTM network to achieve high accuracy in sleep posture classification. And the last one, we want to apply the continual learning in portable posture classification systems to enhance adaptive model learnings and avoid forgetting knowledge when we learn new tasks. So let's deeply discuss and know and discuss about system and methods, and knows how to our system and our model can predict and the sleep posture. And you can see in finger with sleep posture classification system, we have two main components. The first one is a device that collect data, and the next is network It refers to deep learning model to classify the sleep posture. In here, the device will place on a bundle in humans. So human will sleep with various. The device will measure the signal with the various sleep positions such as right, lateral left, lateral right. Will um, surprise and prompt and unsleep. Then the signal will push into deep learning model and it will predict the sleep posture. So the device that we use in our system is uh, there's a size the size of this device with length is 55 millimeters with the width size is 40 millimeter and height is 28 millimeter. The module has comprised of have a more component and have three main components that's the ESP8266 microcontrollers and the accelerometer sensor ADLX345 and the lithium polymer battery can provide continuous usage for up to 8 hours when fully charged. And we use a plastic case to store all component. It's easy to wear in when we want to measure data. Yeah, the next one we'll talk about methods. The main approach, the method is experiment display. It typically is a few sample data. All sample data will store within which will store in a small memory buffer. Yeah. Um, as you can see here, unsleep will refer to all data with the previous task that we want to train model. The all data will the unsleep signal in this picture will we apply the sliding window. We'll get a small window with size. In our study, the optimal size window is 20. So slide window with window's length is 20 will slide uh, in our data set in our signal, and it's put into model our model to predict the task, the label of this task. We have a 12 class, and we to divide into 12 class. We divide into 6 tasks. Each task have two label, different label. So the old data we put into LSTM model to predict the previous task, and it also does the few training sample we have a stored in buffers memory, and the temporal task we use the new data here. Apply slide window to get new data, and combine with concave with the data in buffer and put in LSTM model to predict the temporal task. So continual the base method that we use in our system is continual learning. Continual learning is a basis for intelligent system to accommodate environments. In response to external change, evolutions have empowered humans and other organisms with strong adaptabilities to continually acquire, update, accumulate, and explore knowledge. So we want model to it's not forgot data when predicting when we learn new tasks in the supervised learning in the normal supervised learning model. When P1 model wants to learn new tasks, it's almost forecast. It's almost like forecast the previous knowledge. So we apply to continually. We want to model or not only predict good at new tasks, but also is want to recall or not forget the knowledge of the previous task. In continually method, we have a five base method approach. The first one is regularization based approach with regulation or function regulation regularization. The next is replace by methods, which have three methods: experiment replace, generative replace, and feature replace. The next approach is optimization, which also have a three methods: gradient protection, loss landscape, meta learning. The present the next is the presentation approach with self-supervised learning, pre-train for the downstream tasks, and continual pre-training. And the last one, the architecture approach with parameters localization, model decomposition, and yeah, the last one. So in our study, we focus on um, replaced based method and especially the experiment replace. So replay based methods. The main suburb in the experiment replay it typically stores a few old training samples within a small memory buffer. So there are there are many types of scenario, which is the first one is instant increment learning. Instant increment is all training sample belong to the same task and write in the batch. Domains domain increment learning. The task will have the same data label space but different input distribution. It's like we have two distribution put in our model. Task identify not required. And our study is the task in the next one is also the scenario we use this scenario in our study is a task incremental learning. Task incremental learning is tasks have a disjointed data label space and task identity as provide in post training and testing. Class incremental learning. Class incremental learning tasks have a also have a disjointed data label space, and task identity not, but the task identity not required. Task-free continual learning. Task-free continual learning, tasks have a disjoint. Also, it's the same to task increment learning and class increment learning, but task identities are not provided in either training and testing. Online continual learning. The next one is called online continual learning. Online continual learning in tasks have a disjointed label space. Training sample for each task arise as one pass data downstream, and blur the boundary between continual learning and continual pre-training. It also plus is like the task boundary. We have to calculate the distribution, so the task boundaries are uploaded and characterized by the distinct but overlap data label space. And continual pre-training, what we use the pre-trained data arise sequence space. Uh, arise a sequence space, and the work to improve the performance learning downstream tasks. That is you in the no this that will you in the downstream like the representative task. So the important session that we want to presentation is the result and discussion. The first thing, the data analysis. The data sets were collected from the 16 teenagers in both males and females with various static sleep posture. We have the 12 class. The average age of teenager is 21 plus or minus 1 years old. The data carries information about the sleep postures of people on three axes: X, Y, and Z. And Z. The data contained 192 files, and each file contained 3,000 samples. The training set we have to 12 pupils, and testing set we have to 4 people. Yeah, also class E 12, and the data in here very balanced. Yeah, X class the number of sample in X class is very balanced. So the next one we talk about the loss function. The loss function that we use in the closed entropy is normal, and the famous function that we use in classification tasks in deep learning. It's formulated on in the picture in the slide. So EY is Groucho's also a label, and it has a Y has the output model and its numbers label per patch. The optimizers, all models and were training with ADAM optimizer with 10 above, with 10 and 10 batch. The learning rate will initiate at 0.001, and also apply the early stopping technique when the error does not improves when a trot finds 50 iterations. The importance in this session is metrics. Overall performance is typically averaged by the average accuracies and average increment accuracy. The first thing we have to calculate the average accuracy is denoted by the classification accuracy apparatus on the test set of the G task after increment learnings of the case task. The G task, the D is the smaller or equal to K, and I'm sorry. The first thing we have to calculate is average accuracy into previous task, and the average incremental accuracy we will average on the AI's score in on task. And you can see here AI is present overall performance at the current moment, and AI is overall reflect the variation. Yeah. Here is the training progress. In the slide, I will show the accuracies of model with the different buffer appearing of memory data in the with experiment replace engine. for different with different any size of buffer, but I will show in the buffer size is equal to 0, the buffer size equal to 10, and the last experiment is buffer size is equal to 20. Uh, it's easy to say that to see that the accuracy of the memory data in the with buffer size is 0 is it always 0, because in buffer size that there there have no data on both sides, so that have no data that we can calculate the accuracy. But in the buffer size of 10, we can see the data, the accuracy curve is it tend to down score, and we down score that we decrease score. Is similar to buffer 10, but is dramatically go down. Yeah, it from 100% down to 85%, down to 95%. But in the buffer size with 10, it from the 0.8 0.9 0.998 down to 0.899988. Also, it's also the lost memories. I'm sorry, in here the lost memory data, loss of memory data when it runs for a 6 tasks with any type of buffer. I also visualize the buffer size with 0, 10, and 12. The loss will increase per across training task, as you can see here in the finger. Yeah, the buffer size with the 12, there are more old training sample, so that's why the lost values in the with the buffer size 20 is higher than the lost value of buffer size in with buffer size 10. Averaging, here is the figures of the comparisons of average accuracy with different buffer memory. So the accuracy of model gradually increase as buffer size increase. So you can see here its buffer, the average accuracy is less than 20%, but when you add sample in buffer memory, add more sample in buffer memory, the average accuracy gets higher. And when the buffer 20 is the highest accuracy, the model achieves the highest accuracies of more than 70% with buffer size 20. We also average the forecasting levels of model. It's easy to see when the models have no data in buffer memory. The levels of forecasting of model is evident when the average and forecasting value digits more than 83% with buffer size 0. Meanwhile, when gradually increasing the buffer size, the model has significantly better memorization and achieved 28% less AEF value with buffer size 20. We also the last one we also the visualize and calculate the AIS metrics. The average stand for the average incremental accuracy values of the model through the test. The AI's value increases gradually with X buffer size. If buffer 0 have no data, model model almost forget um, many knowledge that learn previous tasks. But we performed an evaluation on the test sets, and we can see that. You can see the model has good AISA when it reaches values of more than 22%. We also visualize the accuracy across training tasks with different buffer size. With buffer 0, there's no data, so just model just average in individual this task um, because it has no data in memory. For others, a few sample data, for others, a few old sample data which is stored in buffer memory are retrievable to average per task. Normally, the model will forget knowledge of the previous task, the previous task before learning new tasks with people. Our study try to remember previous, try to learn or teach training model that it can remember previous task knowledge and still able to classify news, label its next task. Certainly, it's worth noting that models tend to prioritize recent knowledge over what is learned from the earlier task. In particular, models models when bubble size is small, the model perform poorly when tested on the different tasks. However, as the bubble size increases incrementally, its perform across the task will improve. As you can see here, with buffer the accuracy task will in the buffer with type 10, the accuracy in the previous task will increase. When buffer size reach to 10, reach to 20, we do 15 and 20. It will higher accuracy than the buffer size with smaller buffer size. But in the finger here, people not good at average at the buffer size in the label data in task 2. Task with task identity 2. And here is the accuracy at this task will smaller than other tasks. But on the buffer size 12, it gets performance better than other one. Here is a conversion matrix of RSTM model training with buffer size 0 and buffer size 20. 15. As shown to this figure, the conversion matrix of RSTM model when training with buffer size 0 and 15 is significantly different. In the first finger, in the buffer size 0, the model almost only remembers and classifies the last two classes of the last task. Yeah, last two classes of last task, and that's so the predictions only focus on two classes. Yeah, here is the two classes of the last task: up left, and down. And others classify other label and other class will is not focused on is not predicted. did not predict. In addition, the mod, however, in the second finger, the model classify most the model classify most of will the model classifies most of class model of the class well. In addition, the model still incorrectly predicts quite a lot between the class down left, yeah, the down left, and the right down left and right down, at the rate of 100% and cannot classify the upper postures. So in the discussion, we'll visualize the data when it's passed through the last RSTM model with different buffer, which the here is buffer 0. The data is really classify size 0. The data points are arranged messy and it's difficult to classify to see their separation and classification. In meanwhile, um, in contrast, I don't know, the second data points have a separate distribution and it can be classified more clearly. And this also demonstrates why the model with higher buffer size have a better classification quantity. We have some discussion in our study. Continual learning retains past knowledge while acquiring new skill. In contrast to convent, conventional supervised learning, when new tasks override prior knowledge. We apply this approach to classify sleep positions, achieving strong results with new class without relearning everything from the past. Memory uses memory storage issues can hinder its effectiveness. And we have more the conclusion here. In this study, we applied continual learning to sleeping position classification problem. The result we achieved more than 22% of model accuracy. In addition, the model study the trends in the level forecasting when it's used a replace-based approach and it's specifically experiment replay. In future work, we will we will experiment more with the representative based approach and apply the method on the model in the microcontroller. And thank you so much. If you have some question, you can ask me or give us some comment. So thank you so much. So now I'm gonna the demos of the inference from real time of model. So here is code that I inference. So we have no I have no the device and in here, and so I will inference in our data that are recorded that collected. So I will run the script in command line python's inference.py. The model will predict the time execute when they predict it, and we will show the crouches of class and predict this class in here. The crouches is upright and predicted the right up. I have some the good predicted is right, the crouches is right up and predicted is also right up. I have some so the real time graph predicted prediction. Oh, yeah. The plot maker is the crouches and vision is a green scatter. Um, it we have some many error in here. Also the good predictor, but it's quite good. And here is quite good when they predicted. So this is the end of my presentation. Thank you so much for watching and hearing. So my name is Famida. Thank you so much.